Oh no, more formula, more formula. Anyway, it's just how it is. Okay? So what have we got so far? So far, we have the dispersion relation. Okay, the dispersion relation is, didn't want to do that. Let's just, here's my pointer. Here is the dispersion relation. All right, here it is. You can just rewrite this and just what you want to have it. You want to have the period on the left side. This is done here. And everything, all the other stuff is on the right hand side. And you probably learned all this stuff. That's easy, just a simple transformation of the okay. So now in principle you can calculate the period of your wave, you know the wavelength, and if you know the total water. So now we're going back to the Sage configuration shown here on the left. And the key aspect of Sages is that half the wavelength is the same as this horizontal dimension of your container, your box. And you can make use of that relationship and plug it into that formula. And then you can work out what is the period, okay, knowing what the length L is, the size, the horizontal dimension of your basin, and what is the average water depth. So these two, and there's a factor of 2 in here, and that comes from the fact that only half a wavelength is in there. This formula is known as Merian's formula, but it's only here shown for the base period. So if you know about acoustics and sound theory, this is only the base. It's not the higher harmonics. You can also create some higher harmonics, and then there is some another factor in this formula. Anyway, so this is essentially, if you now have a tank filled with water and you know the dimension, you can exactly work out the period of these. Does this formula work well? Wow, okay, you can also compare this formula with observations. Okay, so how do you now work out the period? Okay, imagine you have a tank and you create a Sage, a standing wave in that tank. You know, essentially all you have to do is you have to estimate the time between two wave crests. Okay, I show it's a little trick of how you can actually get it a little bit better. It might be a little bit tricky if you only look at one period. So this is how the experiment looks like. You see a little tank, a little wave tank, filled with water to 20 centimeters in this example. And we have a little wave shaker. These are little shakers here. You move them back and forth, and you can actually excite a standing wave. Okay? And then, in order to estimate the period, you actually work out the duration of 5 periods, of 5 waves. As you use a watch, okay, a stopwatch to measure the time, and then you just divide it by 5. Yeah, I show you that little video here. All right. This is how you do it. This is how it looks like. Measure the time. Okay. Yeah, and that's brilliant. And this is by doing that, you actually minimize the error if you calculate 5 times and then you divide by 5. All right, yay. This is all super good. No, I didn't want to do that. So thanks for watching. I hope it all makes sense now. You know, it's confusing with formula, but this is only relatively trivial stuff. So why a formula? Just the last thing. Well, it applies to all different type of situations. You know, because you have Sages and as I said, in lakes or basins or in swimming pools and all that. And so you have one formula, but it applies to a whole range of different situations. That's the beauty of formula. Okay, thanks for watching.